Do you remember when I built a bunch of robot dogs? I built a smallish dog which used RC servos, and those are also geared down. It used an inertial measurement unit to measure the angle of the body and corrected the leg angle so that it could pretty much balance and walk properly with only 2 legs on the ground at a time, and this seemed to work okay. These motors and gear ratios were not able to easily be back-driven, so the joints were pretty rigid once they were positioned. But when I built the next 2 robot dogs, they were quite a lot bigger and heavier, so they had a lot more inertia. This meant that I had to use what's known as quasi-direct-drive for the joints, which is the same as a lot of larger commercial robots. This usually involves using the biggest brushless motor you can carry with a very low reduction gearbox so that the joints are back-drivable. I use 10:1 ratio cycloidal drives, and you can watch all the videos about the development in my channel. I then tune the motor driver parameters so that the joints act like a damped spring, a bit like automotive suspension, even though there are no actual springs in the system. The robot's quite heavy, which means it needs to absorb much more load as it moves and the feet hit the ground. So to move dynamically we need this sort of system, which is essentially a virtual damped spring defined by the motor driver position gains and integrator. In my case, the motor drivers are O-drives, which I've used in a lot of projects, and all these parameters can easily be altered to get the best motor response. But what happens when we want an even bigger robot, like the Star Wars AT-AT that I built that I can ride on? Although I used brushed DC motors here, I ended up with a reduction of around 2000 to 1 on each joint, so that there was enough joint torque to carry the robot with me on top. The slightly smaller version I've been building recently also has a similar high reduction, and I'm planning to ride on that one too. The AT-AT only walked at 60 meters an hour, which is around 0.02 miles an hour, but even with faster, higher power motors, there's still so much mass and therefore inertia to absorb as the feet hit the ground, we're pretty much stuck with moving slowly. We could still try to use a low reduction quasi-direct drive for a really big robot to make it more dynamic, but in order to get enough power with such a low reduction would mean having really big brushless motors, so at some point this isn't very practical, and it can't be built with reasonably priced off-the-shelf, easy to obtain parts. So we could use actual springs, but then we're always stuck with a spring, and even low reduction gearboxes are always back-drivable to some extent, so it's really hard to turn off the virtual spring altogether. For future really big projects like the size of the AT-AT, I'd really like to be able to absorb load like having a spring, but also make the joints more rigid or completely rigid when I want to, and do this dynamically on the fly basically, so that I can make the robot stable, so if it tips over I can make one side more rigid and so on to push it back. So in this video I'm going to experiment with building a spring that basically I can turn off when I need to. The main part of the assembly is going to need to be an actuator that can't easily be back driven. So I'm using a ball screw that's got a 5mm lead, and that means for every rotation the nut moves 5mm. I'm also using an O-drive S1 kit with a big brushless motor which is about 2 kilowatts, so this is going to be more than powerful enough to drive quite big robot joints. And to put that into perspective, the AT-AT only used 2 brushed motors per joint, which are about 250 watts each. There's a magnet on the back of the brushless motor and a magnetic encoder on the O-drive S1 itself, so we can control position, velocity or torque. So basically I'm going to build a linear actuator and then try and vary the amount of spring and damping response that we get from it. I 3D printed the parts for this. This is all printed in Polymaker Polylite PLA, which is pretty standard PLA, all with a 0.5mm nozzle, but we're not going to put this on a giant robot, so we don't need to make the assembly particularly tough. To couple the ball screw onto the motor, I'm using one of these CNC couplers that would normally go onto a stepper motor or something, but I've got 1/2 of that, which is still going to fit onto that big ball screw end, and that fits to a bushing which I printed which fits on the motor, so we can put the two straight together. Other off-the-shelf hardware includes this linear slider which has ball bearings in the sliding part, so essentially I made all of this out of pieces from my spares box. As you'd expect, the nut turns on the screw when the motor turns, so that's nice and good, and then we've got this thing that rotates still, which is why we've got a linear slider, so I can attach the two together and that'll stop the nut just spinning around. And the output is 2 bits of 2020, which finally go through some V-wheels to keep them in line. And just to point out, obviously this isn't a great structure for conveying force, although it probably is really strong. Having the output offset on the screw, what we should really have is some more 2020 on the other side, link them together at the top, and then that'll be much better than this offset, and probably make some bits out of aluminium or steel. I wonder how strong it is. Right, the actuator's under the table. I'm going to just try and lift me and see if it's strong enough for giant walking robots that I can ride on. Oh, yep, no problems there.
Yep.
And that's also really quite quick for a linear actuator driven by a screw. Normally they're pretty slow, so this is going to be great for giant robots that need to move dynamically and react really quickly to whatever sensor inputs.
So it's super quick. We've got 50 volts of lipos here and a 100 kV motor, so we're getting in excess of 3000 RPM on the motor, and then 5mm lead, so every revolution is 5mm of travel. So it goes really quick. Obviously this isn't really back-drivable. I can push this backwards if I push the top, but all I have to do is put my finger on the motor, and I can't push it anymore because obviously it's really hard to drive a nut back down a screw without the screw turning. So with a 2 kilowatt motor, this should be completely rigid if we want to back drive it, which is great because it means I can turn off my virtual spring. What we need to do next though is see actually if we can make a virtual spring and make this back drivable essentially a little bit when we need it to be. So we need some sort of sensor.
So I've got a load cell, which is this metal thing. There's an amp board, which is the SparkFun NAU7802 quick scale board, which gives us data over I2C that we can read with a microcontroller. There are many load cells available to buy, which are basically bits of metal rated to a specific load. They generally have strain gauges attached to them which can detect minute flex in the thing they are attached to. These are generally arranged in a Wheatstone bridge, and this is a balanced voltage divider which makes it very accurate for low-level signals. If you look for load cells to purchase, they generally come with a cheaper amp and interface board. These are fine for weighing scale applications, but they aren't very fast. The SparkFun board can read the data up to 320 times a second, so that'll make our system much more responsive.
So you'll notice the load cell is basically a solid block of metal. It has got this cutout in it, so it can be bent, but you can't really see it being bent. It's nothing like a spring, and I can actually get the data out for this. There is a bit of noise basically when it's idling, but if I bend it we get quite a big deviation, and we can see that we're putting quite a lot of load on that just with my hands. Now this one's rated at 100 kilograms. We can get smaller ones, but this is going to be good for giant walking robots, I think. Yeah, it's much better if I bend it over the edge of a table. You can see that data much more clearly, even though I'm really just holding this block of metal with my hands and hardly bending it. So if this was mounted on a mechanical assembly and we bent it by the robot jumping on the ground carrying me, we probably get much bigger deviations. Obviously I'm not putting anywhere near 100 kilograms on the end of this.
Yes, very simply, it's going on the end of the actuator so we can measure the load and try and make the actuator respond the way we want.
Have you ever thought about getting metal parts made, like these metal plates that I used in my last project? Well, I got these made at PCBWay, who are the sponsor of this video. PCBWay is a one-stop shop for PCB manufacturing, assembly, but also other types of manufacturing services, including contract manufacturing, all under the same roof. PCBWay manufactures all sorts of printed circuit boards, but PCBWay don't just make PCBs. They also provide parts manufacturing services, including online CNC machining, sheet metal fabrication, 3D printing, and injection molding. PCBWay's 3D printing services include SLS, SLA, DLP, FDM in a variety of materials, including various resins, nylon, PLA, ABS, TPU, PEEK, and more. There are various surface finishes available, including painting and even electroplating. PCBWay have an open source community called Shared Projects, where many people have uploaded their project source so you can build the project too. If there's a part like the PCB that PCBWay can manufacture, you can buy this directly from the project page, otherwise the other source files are included as downloads. Project of the week this week is the Seanville Tiny Model Train Christmas Ornament Controller, which is a hanging Christmas ornament with some wireless LEDs that move along a tiny track like a train, and even a sun that moves across the sky. Find out more now at PCBWay.com, and I'll put that link in the description as well. So with that attached to a mechanical assembly, we now get a much bigger deviation in the data compared to the noise at least, so we should have no problem driving the motor with that and being able to make it back drivable when we want it. The only slight question is this going to be quick enough, this whole system, to act like an actual spring? Obviously we've got that teensy microcontroller in the middle, which is talking back to the motor over CAN bus, and we've got that I2C board reading the load cell, so the whole thing's in a big loop. Now we're running at 300 Hz, which is the fastest the load cell board would go, but is that going to be quick enough? Ideally we'd take the teensy out and I'd write custom firmware for the O drive to read the load cell directly from the I2C board, but I'm not that good at STM32 code, and I'd really like to build this off-the-shelf parts. So now I'm just going to take the value from the load cell and basically stick it straight on the motor. I've got a little pot here so I can turn it up and I can scale it. So at the moment, completely rigid. If we turn this up a little bit, and it starts to get back-drivable a bit. It's still quite stiff. If I turn it up a bit more. Well, it feels quite springy actually. Oh yeah, I only need a light touch. Can see a bit of noise in the motor, but it only needs the lightest touch. And that's actually quite responsive. That's probably responsive enough to be useful. I wasn't sure if I'd hit it and then there'd be a delay, you know, with this whole loop going through the teensy and back through the CAN bus. I did turn the CAN bus up to a megabit. But yeah, that's actually quite good. But we need to turn it up the other way and see what happens if this was a leg and the robot was on top putting its weight down. Right, let's try it this way up. Let's get all these wires out of the way. Alright, where's my pot? So, immediately, yeah, we get some oscillations. If I just hold it in the air, it's fine, but then if I push it down, that's not going to be much use. Of course, what's happening is this is getting a load applied to it, then it's retracting because of the load, and then there's no load, so then it comes back again, and then the whole thing carries on. And this table's quite bouncy as well, which doesn't help. Now, obviously, a spring will oscillate, the thing will bounce there for a bit if it was an actual spring, but this is a spring effectively driven by a massively high power motor, so it just carries on forever, and there's no mechanical damping. Right, one possible problem is that this works in reverse as well, because the load cell gives us both positive and negative data, which is probably why we've got some problems with oscillations. So we're going to take away the negative data so we can't do this, and we can only get this part of it, and then we'll see what we need to do.
So I just did a simple constrain in Arduino code that takes away the negative values so it can only drive it in one direction. Now this has helped a bit with the oscillations, but as soon as I turn the gain up, then basically it's the same story for pretty much the same reasons. What we really need to do is simulate a dash pot or an air pot, which is what we have in a mechanical suspension system. These add friction by pushing liquid or air through small holes, so your car doesn't keep bouncing after it goes over a bump, basically. We need to do this in code though, and I've done this a lot for animatronic and control systems before, including the controls of the Omni bikes to make acceleration and deceleration smoother. I previously made an entire video about this that you should check out. I built an animatronic head with filtering on all the motions. I did this by bookmarking the previous value in the loop and using a larger part of that value added to a much smaller part of any new values as they came along. This means that the resulting variable can't change too quickly. We do get a fairly quick initial response though, followed by a curved off response towards the end of the change in the initial input. This is quite similar to mechanical damping in a dashpot as friction builds up and the response slows down.
So I've now got one pot for gain as we had before. And I've got another one to mix some of that filter in, so it does make it less responsive. Right, so let's have some gain. And now I should be able to turn off the oscillations with the damping, so let's turn up a bit more. So actually, yeah, that's pretty good. It doesn't oscillate anymore. If I turn it right up, it's not as responsive and I have to push a bit harder. We turn that down just till it oscillates. And that's pretty good. See what happens if I just drop this, is it quick enough? So it absorbs load, but you can see there's a little oscillation to start with, where there's a little bounce. Let's just turn everything off completely, so now it's rigid again. And that is the bounce that we get anyway, from both the table and probably this load cell sticking out, which is slightly flexible of course, because it's got holes in it and is meant to be flexed. So So that little bit of bounce means it's not quite responsive enough to absorb the load, so our loop's not quick enough basically, but we have slowed it down by turning up the damping.
So I thought I'd just remove the ability for it to move out at all, and it only moves in as you apply more and more force. So now it's moving at full speed with no damping, but it can't oscillate because it can't move back out again.
So still some vibrations when we first drop it, when it bounces before it can respond, which means the latency at least is too high, reading the load cell and writing that data back to the motor. But realistically, how quick are big robots with me riding on going to take steps? Obviously when I drop it, that's quite quick, but if it's a giant robot taking steps, it's probably going to be much slower. Right, so that's rigid, and now if we turn up the gain a bit, so with much more load on it, we don't need as much gain because we don't need to amplify the signal so much, and therefore we don't need so much damping, so we get actually a pretty good response. Let me just turn that up a little bit more. I do have the tiniest amount of damping, but actually that's pretty responsive. So if you imagine a giant robot taking steps, it's probably going to be quite slow, and even quicker than that. That is absorbing load enough to be useful. So for small robots like OpenDog 3 and those that still need to absorb load, we can use O drives with quasi-direct-drive, a low reduction, to absorb load and make them dynamic. But for big robots, we can just use the same actuator with a ball screw so it's strong enough and apparently quick enough, and then just use a load cell to absorb the load to make them more dynamic. So what would you like to see next? An AT-ST I can ride on, or a life-size ED 209? Put your answers in the comments. And if you like this sort of thing, then check out my Patreon campaign, and patrons and YouTube channel members can get access to sneak peeks and pictures of what's coming up and be part of all that discussion.